Welcome to this module of Professor Messer's free CompTIA Network Plus certification training course, the online training course that's as wild as a June bug on a string. I'm James Messer, and in this module we're going to talk about the properties of routing. We're going to go through these requirements from our N10-004 section 1.6 certification, where we need to explain the purpose and properties of routing. So there's a number of routing technologies we'll discuss. We'll talk about the difference between IGP and EGP. We'll talk about static versus dynamic routes. We'll talk about the next hop and how important it is. Look at some routing tables, and finally discuss convergence and why convergence is an important thing to consider when talking about routing. Let's talk about why we would need routing protocols to begin with. This is something as you're going through Network Plus and trying to figure out, why do I have to understand all of this? Well, this is why. We have to know that a router's job is to get packets from one network and send it to another network. At its very basic level, that's all a router is really responsible for. These are usually networks that are not directly connected. These are usually networks where we are on one side of the internet and we need to somehow talk to a network that is on the other side of the internet somewhere. We don't even know exactly where that network might be. So routers have a very simple process. They take place on an individual level, but being able to connect them, multiple routers over long distances, becomes a little more complex. So our routers really need to know how to get anywhere that we might need to go. Fortunately, we've got these routing protocols. Our previous video talked about what some of those routing protocols are. But those routing protocols are extremely important because they give the router the smarts that it needs to know to be able to take a packet in one interface and figure out where to send that packet. Where should it be going from here? And so those routing protocols allow us to do that. Here's an example of this. Let's say that we need to talk across the network. And we're on these networks here, this 192.168 network, and we have a router here that's connecting to all of these networks. Now, how does that router know where to send information? How does it know how to get packet in one interface, and how does it determine what to do with that information once it's received it? Well, fortunately, inside the router is a big table, just a big list of networks, if you will, and that list of networks helps the router know where it should send traffic. Now, this is a lot of numbers, but let me explain to you what we're looking at here. This is a routing table from my computer, which essentially says if I'm going to 0.0.0.0, which is a default route, send it out this IP address on my machine. And that happens to be this 192.168.0.8 interface on my machine, and it happens to be connecting to a network that has this gateway on it. And that's the link whenever I need to talk out to the internet, that it sends everything out to the internet. Now, if I needed to talk to an internal network, let's say there's a 3.0 network here, it sends it out a different interface, 192.168.3.1, which is very different than the 192.168.0.8 interface. Multiple interfaces in my machine. And so this routing table does a determination based on the best way to get to that range of IP addresses and where it should go. So it's nice to have these routing tables there. We're going to come back and look at a routing table example in just a bit and break this down a little bit further. Before we start talking about the details of routing, let's talk about these concepts of IGP and EGP. Now, before we really get into the I and EGP of it, let's talk about something called an autonomous system, an AS. Now, autonomous means that it is something that is an independent entity. It is something that works all independently of anything else that happens to be out there. This is something that's a very important concept to consider in routing, because routers are usually part of an autonomous system. There's usually a bunch of devices that work autonomously. And so usually there is a set of IP routes under common control. This is what's written in RFC 1930. There's a section 3 with definitions that says an AS is a connected group of one or more IP prefixes run by one or more network operators, which has a single and clearly defined routing policy. Usually an entire organization is a single AS. Usually individual organizations are individual ASs. That is one way that we talk about routing protocols, and the way they operate between each other is to describe them as a single AS. You'll see this come up quite a bit. An important point of reference for what we're about to talk about, interior gateway protocols and exterior gateway protocols make use of this concept of autonomous systems. And so keep that in mind as we go through these next couple of slides. We'll start with Interior Gateway Protocol. An IGP is used within a single autonomous system. So let's say you're a single organization. You all maintain your own routing in your organization. You really don't route outside of your organization. It's just you're in charge of the routes for your network. That means you are a single AS, which means the Interior Gateway Protocols is what you would use in your environment. This is not designed, these types of IGP protocols are not designed to route between autonomous systems. It's just inside your own little environment. There's a completely separate set of protocols called Exterior Gateway Protocols that allow different ASs to communicate between each other. For an internal gateway protocol, we have these types of protocols, and we've already talked about these in a previous module, but OSPF, ISIS, RIP, RIP version 2, and EIGRP are some very good examples of interior gateway protocols, protocols that would use inside of your organization to be able to route. And these are protocols and types of protocols that you will use every day because that's what you're using inside of your environment. Now, if there's internal gateway protocols, there is certainly exterior gateway protocols that we can look at. This is what allows us to route between these autonomous systems. Because autonomous systems, you may have no idea how somebody else routes inside their own AS, but we don't care because we have these great exterior gateway protocols that at least allow us to talk at a high level between each other. So we can manage our own routing internally and not even care about anybody else, but still be able to talk with the rest of the world. Isn't that great? One good example of this is the default routing protocol for the internet called BGP. Almost everybody is using BGP as their EGP, which means I can do anything I want routing internally to my network. And I know I can talk to the internet because facing outside of my network of my AS, my autonomous system, I'm using BGP to talk to everybody else that's out there. Here's a good example of this. I've drawn a picture of 4 different companies: Company A, Company B, Company C, and Company D. Now within these companies, they're all using their own internal gateway protocols to communicate. So they've got, one might be running RIP, another one might be running OSPF, another one might be running EIGRP, and Company D down here is running RIP version 2. They can all be very different in the way they operate, but they may still need to talk to each other over the internet. And that's why we have BGP, this exterior gateway protocol, to be able to handle that communication. So that's a very good example of how we can use IGPs internally within our own autonomous systems, but still be able to talk between our autonomous systems with these exterior gateway protocols. There's a number of properties we need to keep in mind with routing that are important for the Network Plus exam, and one is called static routing, and another is called dynamic routing. Now, dynamic routing is, like the name implies, very automatic and very hands-off. That means that all routers are able to make changes to the routes all on the fly. All the routing decisions are handled by RIP, they're handled by OSPF. They're able to decide at any point in time when things change on the network how the traffic should route around that. That's a little bit different than a static routing, which is a manual process, which you manually put inside your router. You tell your router, if you see traffic coming from this interface and it's going to this network, always go this direction. And that's it. You've essentially programmed your router to do this statically, and it's always going to do that way. This is something you do if you want to set up a default route to the internet, for instance. Take anything that's not on our internal network and send it out to the internet through this link. And you've manually programmed that into your router as a static route. Whenever you look at static routing and dynamic routing, you're going to see this term called the next hop. You need to define the next hop because your router really doesn't care about something that's on the other side of the network. The packet comes into the router, we do something with it, the packet goes out of the router. That's all it cares about. And so this idea of a next hop is a very important piece of information. Your router says, I need to look at where this is going. What's the next hop for this? And then it sends it on its way. That's the whole reason your router exists in this world. So it determines where it's going. It goes out to that next hop. Now it's probably going to keep going down some different hops because once it gets to that next hop, it's really going to a router, which then makes another determination of where it goes from there. And your router doesn't care. It's just sending it on to the next hop. Here is a routing table. It's a little bit different than the routing table we were looking at earlier. But this is one where we have these next hops in there. We have anything that might be going, let's look down here to 192.168.3.0. It has a gateway on this network of 192.168.3.1. That's the interface. That's our next hop. We're going to send it out this interface to this next hop. we're going to get to our 0.1. If we need to go to anything that's on 192.168.0.0, then we go out 192.168.0.8, which is the interface in our machine, to our next hop of 192.168.0.1. Notice there are metric numbers here too that are used. This is how far we need to go to get to those particular networks. The lower the metric, the more we will use that link. That is our preferred link at a lower number. The higher numbers are less preferred. So we're going to use the low numbers first, and we're going to go up our list from there. The idea is that our router knows what that next hop is, and it's going to use its routing table to make the decision of where it goes down the line. Another important routing characteristic to consider is something called convergence. You usually think about convergence when you're initially configuring or setting up a network with a routing protocol. And that's because convergence is something that happens when two or more things come together. Your networks are never exactly the way they are today as they're going to be tomorrow. Networks may go up or down, routers may come up and down, a new link may come onto the network. Things are constantly changing. And so when that change happens, the network has to converge. We notice a link change because the router is going to recognize that something changed. The router is either not hearing from another router that's out on the network. Maybe a third router said, we noticed this link went away. Something happened that your router noticed that something changed. So the router has to process the update. And it has to calculate now where the new route might be based on the change that it just got. And finally, it begins updating its tables and begins sending traffic out based on what the new route is. Now, depending on the routing protocol you're using, that update might take seconds. It might take minutes for that routing update to occur. Now, during that time, as this convergence is taking place, what happens to your packets that are going into your router and they don't know where they're going? Well, your router may have a bad route. It might still be trying to send it to a network that no longer exists, or the traffic might just time out. We might just the packets might just fall all over the floor. The router doesn't know what to do with them, throws them out completely. And in those situations, that just happens to be the way the routing protocol works. And you made that decision. When you decided to use RIP, you knew the convergence times would be long. Or maybe you said, I need fast convergence, we're going to use OSPF. It's a little bit more difficult to understand OSPF and get it configured, but ultimately it's going to help us because it's a much faster convergence time, and that's important for what we're doing on our network. Now, if a link state is changing in the middle of a convergence, a route goes up, your router recognizes it, and while your router is trying to make the change, the route goes down, and then it goes up, and then it goes down, and your route begins flapping. Keeps happening over and over, and you may find that your network keeps changing and your routes never get updated because a route keeps flapping up and down again. So you need to know the characteristics of your routing protocol and recognize how this reacts when something like flapping takes place and what you can expect. There are a number of timers in almost every routing protocol that allow you to adjust how long it waits for certain things to happen. Maybe it's just adjustments of different timers that are going to make that routing protocol work a little bit better or a little bit worse for what you're doing. Let's review how much we remember about these routing technologies and these properties of routing. Give me an example of an interior gateway protocol. Now, you remember these are gateway protocols that we use inside of our autonomous systems. These are used inside of our own organizations to route things. There are a number of them there, and the ones that I have are RIP, RIP version 2, EIGRP, OSPF, and ISIS. There are also a number of other routing technologies that are out there, but this is some that we have that we need to know for our Network Plus certification. Which routing method automatically determines the correct route? Is it a dynamic route or a static route? Now, the key word here is automatic. And if you saw that, you would know that it's a dynamic route that automatically determines where traffic should go, and it's based on the characteristics that are occurring on your network in real time. Now, what routing metric determines which interface a packet should take to reach its destination? There's an important metric that your router looks at a packet, and now it needs to know where to go. Where does it go? It goes to the next hop. An important idea behind routing tables and what routers do is that next hop. And that covers our requirements for the N10-004 Network Plus exam in section 1.6, where we've gone through IGP and EGP. We've looked at static versus dynamic, and we've looked at routing tables and how they use next hops, how they determine what path to go down, and how convergence applies to these routing protocols, and how fast a route can converge once something changes on the network. For many more Network Plus certification videos, for our message boards and much more, you can visit our website, freenetworkplus.com.